In this video, I want to take a look at exam revision for sequences and series. So all we're going to do is just take a look at some exam style questions for sequences and series. So what we're looking at here is, for example, arithmetic sequences and series, geometric sequences and series, recurrence relations, sigma notation, and modeling with series. So like always, pause the video, have a look at the questions they appear, and then double check that your solution matches what we get on the screen. Other than that though, I think that's everything that we need here to get started. So let's begin now with question 1. Starting off with the very first question now, so we've got a geometric series here, and we're told the first term of this geometric series is 80, and then the sum to infinity of the series is 400. So for the first part, I want to show that r equals 0.8. So for part A then, so here I want to show that r equals 0.8. How do we do this? Well, to begin with, let's just note down the information that we already have. So I know the first term of this geometric series is 80. So we use a here to represent the first term. So a equals 80. And we also know then that the sum to infinity of this series here is 400. So the sum to infinity is equal to 400. Okay. Now, the formula then for the sum to infinity, we do know that. So the sum to infinity here, that's given as a over 1 minus r. Now, we know the value here of this sum, this summation here to infinity, that's 400. We know the value of a, so we've got everything that we need here then to show that r equals 0.8. So I've got 400. That is equal to a, which is 80. That's divided then by 1 minus r. So now to begin with here, I want to get rid of this 1 minus r. So I'm going to times both sides by 1 minus r here. So get 400 bracket 1 minus r. And then on the right hand side here, we get left with 80, this numerator. That's equal to 80. So now to get 1 minus r on its own here, I'm going to divide both sides by 400. To get 1 minus r is equal to 80 over 400. That's the same as 8 over 40, which is the same as 1/5. So get 1 over 5 there. And then finally, if I want r here, that's going to be equal then to 1 minus 1/5. And that would give us 4/5 there. Okay, or 4 over 5, which is the same thing as r equals 0.8 there. Okay. That's equal to 0.8 as required. So that's part A done. So now for part B, let's do this over here. We want to calculate the sum of the first 8 terms. So we want to find S8 here. Okay, so we're going to need the formula then for the sum of the first n terms. So using Sn, so the sum of the first n terms. So the formula here then for the sum of the first n terms, that's given as a times 1 minus r to the power of m. That's all over 1 minus r. So we need S8, the sum of the first 8 terms. So therefore S8, that's simply going to be a, which is 80, times by 1 minus r. So r here is 4/5 or 0.8. So 1 minus 4 over 5. And that then is to the power of 8 here, because n equals 8. That's the power of 8. And then all over 1 minus r. Or in this case, then that's going to be 1 minus 4 over 5. So that'll give me 1/5 there. Okay. So all you need to do here then is just put this into your calculator. And if you do this correctly, what you should get then is 332. Get 332.9 there. Okay, and I've rounded that to 1 decimal place. But anything sensible, it doesn't give, a certain degree of accuracy here. So anything sensible is absolutely fine there. So that's the solution to B. And then finally, we've got part C here. Now we're going to need a bit more room. So let me just quickly clear the screen here for part C. So for part C then, it says the sum of the first n terms of the series is greater than 280. Find the smallest possible value of n. So this statement here actually forms an inequality. So what we're saying then is we need Sm is strictly greater than 280. Okay, this statement here is the same as this inequality here. Now, we already know the formula here for the sum to the first n terms. We use that in part B. So Sm, that's equal to A times 1 minus r to the power of m, all over 1 minus r. And here then, A is equal to 80, that's our first term. And r in this case, that is the common ratio here, which is 4/5. Okay, 4/5 there. So what I'm going to do now is use this result here for Sm. I'm also going to substitute these values of A and R in and then form this inequality here. So altogether, what that would look like then is I'd get 80 times 1 minus R, where R equals 4/5, so 4/5. And that's the power of n. And that's all over 1 minus R, so 1 minus 4/5, that would give me 1/5 again. And this here then is strictly greater than 280. Like so. So now, if we're dividing by 1/5 here, that's the same as times in the numerator by 5. So 80 times by 5 is 400. So here I'm going to get 400 times 1 minus 4/5 to the power of n. And that's strictly greater than 280. So now I want to get rid of this 400 here, so we can do that by dividing both sides by 400. So we get 1 minus 4/5 to the power of m. And that's strictly greater than 280 divided by 400. Like so. So now, in this case here, I want to make this positive, so I'm going to add that to both sides. What I'm also going to do here is subtract 280 over 400 from both sides as well. We get 1 minus 280 over 400. And that is greater than 4/5 to the power of m. So 1 minus 280 over 400, that simplifies to 3/10. So therefore what we've got here then is 3/10 is greater than 4/5 to the power of m. So this inequality here, well, if 3/10 is greater than 4/5 to the power of n, we can write this then as, put it up here, so this is the same thing then as 4/5 to the power of n being less than 3/10. Okay, they're the same thing, but I think this is a little bit easier to work with now. So from here then, we now need to find the value of n. So what I'm going to do here is take logs of both sides. And then obviously, with us having a power here, we can use the power rule for logarithms. So I can bring the n down in front. So we get n log 4/5. Put these in brackets here. So n log 4/5 is less than log 3/10. Okay. So now what I'm going to do here is I'm going to divide both sides by log 4/5. Now, you need to be very careful here. So in this case here then, this logarithmic value, so log 4/5, if you put that into your calculator, so log of 0.8, what you'll find is you actually get a negative value. And this is important because what's going to happen now is my inequality here will flip. So rather than it being less than, it will now become greater than. So in that case then, we get that n must be strictly greater than log 3/10 divided by log of 4/5, so 4/5. Okay, like so. So if you put this into your calculator here, so log of 0.3, and then divide that by log of 0.8, then what I get here is 5.395507 and so on. So that is approximately, let's say, 5.4. Okay, so n must be greater than 5.3955, so on and so on. Now, n here must be an integer value because we're looking for the sum of the first n terms. So n is an integer. So in that case, then what we have to do here is round up. We can't round down. If I round down, then that would mean that the sum of the first n terms is not greater than 280. It has to be at least 5.3955 or greater than 5.3955, I should say. So in that case, then we round this value up. So therefore n equals 6, because we need to round that value up. So in that case, then the sum of the first 6 terms of the series is greater than 280. Okay, so in that case, the smallest possible value of n is n equals 6, and that gives the solution there to question 1. Moving on to question 2 now, where we have a sequence a1, a2, a3, and this carries on, and this is defined by a1 equals k, where k is a constant, and then a of n plus 1 is equal to 3 lots of an minus 1. So what I've got here is a recurrence relation, where the next term is equal to 3 lots of the previous term minus 1. So for the first part here, part A, we want to simply find a2. So a1 here is equal to k, where k is a constant. So a2 in that case then, well, that's when n equals 1. So a1 plus 1 is a2. So that's equal to 3 lots of a1. So 3 lots of the previous term minus 1. So we get 3a1 minus 1. And a1 here is equal to k, where k is a constant. So we simply get 3k minus 1. Okay, that's all we need there for part A, nice and straightforward. Now, for part B then, it says show that A3 is equal to 9k minus 4. So for A3 then, that would be equal to 3 lots of the previous term, so 3 lots of A2, and then we subtract 1. We get 3A2 minus 1. And in this case, then we're going to get 3 lots of A2, which is 3k minus 1. So 3 lots of 3k minus 1. And don't forget the minus 1 here as well. And then if we evaluate this here, or simplify, I should say, 3 times 3k is 9k. 3 times minus 1 is minus 3. We've also got minus 1 here, so minus 3 minus 1 gives us minus 4 there. Okay, and notice we get A3 equals 9k minus 4 as required. So as required there. So that's part B done. And then finally for part C here, it says show that the summation here, so this is the summation of AR from R equals 1 to 4, is a multiple of 2. So we've got this sigma notation here. So this represents a summation. What it actually represents here is the summation of the first 4 terms of this recurrence relation. So this summation here, let me just write it down, from R equals 1 to 4 of AR. This is equal then to A1 plus A2 plus A3, and then finally plus A4. So notice here already we've got A1, that's k, we've got A2, 3k minus 1. We've also got A3, 9k minus 4, but I don't have A4, okay? So basically all we're looking to do here is add these 4 terms together, and then if this is a multiple of 2, we should be able to factor a 2 out from this simplified expression here. Okay, so let's find A4 to begin with. So A4 here, well, that's 3 lots of the previous term minus 1. So that's 3 lots of A3 minus 1. So A3 here, that's 9k minus 4. So we get 3 lots of 9k minus 4. And don't forget the minus 1 as well. So then if we simplify this here, 3 times 9k is 27k. 3 times minus 4 is minus 12, minus the 1, and that gives us minus 13 there. Okay, so that is A4 there. So we've got all the individual terms that we need here. I've got A1, A2, A3, and then finally A4 as well. So now we can find the summation here. So from R equals 1 to 4 of AR, this is equal then. So we've got K. I've also got 3k minus 1 for A2. For A3, that is 9k minus 4. So plus 9k minus 4. And then finally A4 is 27k minus 13. So all I want to do here then is simplify this right hand side. I've got k plus 3k, so that's 4k, plus 9k is 13k, and then plus 27k, that gives me 40k. Okay. We've also got minus 1, minus 4, so that's minus 5, minus 13, and that gives me minus 18 there. Okay. So like we said, if this is a multiple of 2, what we should be able to do here is factor out a 2, which we can indeed do here. And if we can factor out the 2, what that means then is this summation must be a multiple of 2. We can write this here then as 2 lots of 20k minus 9. So therefore, the summation from r equals 1 to 4 of AR is a multiple of 2. Okay. And there we have it. So that gives us the solution there to question 2. Moving on to question 3 now, where we have the 4th term of an arithmetic series that's given as 24, and the 10th term is 66. So for the first part here, part A, we want to find the first term and the common difference of the series. So part A then, what we know is U4, the 4th term in this arithmetic series, is 24. So U4 is 24. And we also know that U10, the 10th term in this arithmetic series, that's 66. Okay. So what's the formula here then for the nth term of an arithmetic series? So UN, this is the nth term here. So that is equal to A plus n minus 1 times D here, the common difference. So in that case then, for U4, so U4 here, that's equal to A plus, so n here then would be 4, so it's going to be 4 minus 1 times by D, so that would give me A plus 3D here. And we know U4 in that case is 24, so that is equal to 24. So A plus 3D is equal to 24. Doing the same now for U10. So the 10th term here, that would be equal to A plus 10 minus 1 times D, so that would be A plus 9D. And this here we know is equal to 66. So in that case then, A plus 9D is equal to 66. So now, what I'm going to do here is rearrange both of these so that A is the subject, and then I can set them equal to each other. So in this case, for this first equation here, this would be A equals 24 minus 3D. And then for this equation here, this would be A equals 66 minus 9D. Like so. And now, because they're both A equals here, I can just equate the right-hand side here for both of these. So therefore, 24 minus 3D is equal to 66 minus 9D. And then from here, all I need to do now is solve this equation here for D. So add 9D to both sides, so I get 24. So minus 3D plus 9D, that would be 6D. And that is equal to 66. Now subtract here 24 off both sides. So we get 60 equals 66 minus 24. So that would give us 42 there. And then finally, divide both sides by 6. And therefore, D is equal to 42 divided by 6. In that case, then, D is equal to 7. Okay. So the common difference of this series here is 7. But we also need the first term. So we now need A. And then to find A, we can substitute that into either this equation here or this equation here. Obviously, it doesn't matter which one you do. I think the easier one is this equation here. So in that case then, A is equal to 24 minus 3 times 7. 3 times 7 is 21, so 24 minus 21 gives us 3 there. Okay, so the first term in this series is 3, and the common difference is 7. So that's part A done. So for part B then, we should have enough room over here for part B. Let me just split this off a little bit here. Like so. So for part B then, we're looking for the sum of the first 10 terms of the series. So we need S10. So to find S10, we need the sum of the first n terms formula. And this is for an arithmetic series here. So Sn, that is equal to n over 2. We have n over 2 times that by 2a. And then we have plus n minus 1d. Like so. Okay. Obviously, if you do know the last term, you can use the other formula here for the sum of the first n terms. But because I don't have the, in fact, I do have the 10th term here, so we can actually use that. So let me just rewrite that. So that is n over 2, and then we have a plus L. Okay. That's also the formula then for the sum of the first n terms, if you know the first term and the last term. So because my 10th term here is 66, and we're looking for the sum of the first 10 terms, I can also use this formula here. Don't matter which one you use, but this one is just slightly easier to work with. So in that case then, S10, that's going to be 10 over 2. And we times that by A, which is 3, plus L. So L here is the last term, so that's 66. So what I get then is 5 times 69 here, and that is equal to 345. Okay. And there we go. So that's all we need there for part B. Like I said, you can use either of these here, but seeing as we already have the last term, the 10th term in that series, we can just use this different version here. That's a little bit easier to work with. Okay. So that's part B done. And then finally for part C here, there's a little bit of work involved for part C. So all I'm going to do then is just clear the screen. So for part C now, it says the sum of the first n terms is 4,518. Find the value of n. So the sum of the first n terms here is 4,518. So what we're saying then is Sm is equal to 4,518. Okay. So let's use the formula then for the sum of the first n terms. So we're going to use here, so using Sn, that equals n over 2 times 2a plus n minus 1 d. Okay. So in that case then, we have n over 2, 2a, so a is 3, so that's 2 times 3, so that's 6, plus, so now I've got n minus 1 times d. Obviously, we don't know what n is, that's what we're looking to find the value of. I do know what d is, that's our common difference, which is 7, so I get plus 7 lots of n minus 1 here, 7 lots of n minus 1, and that is equal then to 4,518. Okay, what I'm going to do now is I'm going to get rid of this denominator of 2 here, so I'm going to times both sides by 2. So on the left hand side we'll get n times 6 plus 7 lots of n minus 1. Okay, and that is equal then to 4,518 times by 2. That would give me 9,036. So we get 9,036 there. So now, if we just think about this for a moment, I've got n lots of 6 plus 7 lots of n minus 1. So if we expand this out here first to begin with, I get 7n minus 7. So minus 7 plus 6, that's minus 1. I've got n lots here of 7n minus 1. And that is equal to 9,036. So what I'm going to get here then is a quadratic equation. So if I think about expanding this out here, I'm going to get 7n squared. I get 7n squared minus n. And what I'm also going to do here now is subtract 9,036 off both sides so that our quadratic equation here is equal to 0. So we get minus 9,036, and that is equal to 0. Okay. Now, what we're looking for here is to solve this quadratic equation to find the value of m. And by looking at this quadratic here, it's not immediately obvious whether this will factorize. So it's up to you how you go about solving this quadratic here. You can go straight into the quadratic formula. That's absolutely fine. You can try and attempt to factorize this here, but I don't think this is the easiest to try and factorize by hand. Or you could use a graphical calculator. So if your calculator can solve a quadratic like this and give you the solutions, that's also fine. You can find the factorized form going backwards from that. So if I use my calculator here, what I get then is that n equals 36. Okay. What I know then is if I factorize this here, I'm going to get n minus 36 is equal to 0. And then for my other solution, I get minus 251 over 7. So working backwards from that, I can see then that my other bracket here must be 7n plus 251. Okay, like so. That's my factorized form there. So I get bracket 7n plus 251, bracket n minus 36. From here then, like we said, we get two solutions for n. This solution here, well, that would be negative. Obviously, n must be positive here, the sum of the first n terms. So this solution we omit, we don't include that. That means then that my solution here for n is n equals 36. Okay. And that's what you should get there. Now, like I said, you could do the quadratic formula. That's absolutely fine. And either way, if you use the quadratic formula, or you do it like this here, like I've done, working backwards from a solution from your calculator, either way, you should get 36 there for n. Okay. And there you have it. So that's the solution there to question 3. Moving on to question 4 now, where we have a question here on sigma notation. So what we've been given is this summation. So 5 times 2 to the power of r from r equals 1 to k, that is equal to 163,830. So for the first part, I want to show that k is equal to this number here. Now, this can be quite tricky. You've never really seen a question like this before. However, if you've seen one like this before, you'll recognize they all follow a very similar pattern. So what you need to recognize here is that 5 times 2 to the power of r, this here forms a geometric series. And if you're not sure why, think about the first few terms here. So when r equals 1, what do we get here then? Well, that's 5 times 2 to the power 1, so that's 2. 5 times 2 is 10. What about then when r equals 2? Well, in that case then, I get 5 times 2 squared. 2 squared is 4. 5 times 4 is 20. And then finally, we'll look at one more term here when r equals 3. I get 5 times 2 cubed. 2 cubed is 8. 5 times 8 gives me 40. So what we can see here then is we have a geometric series where we are doubling each time. So we're timesing by 2, timesing by 2 again. So in this case here then, my common ratio r is equal to 2. And my first term a is equal to 10. Okay. So here, this now is a geometric series. And we're looking at the sum of the first k terms. So what we're saying here then is sk, the sum of the first k terms, is equal to this number here. We get 163,830. So because this is a geometric series here, we need the formula then for the sum of the first k terms. So using sk is equal then to a times 1 minus r. So be careful here, it's not to the power of n, but to the power of k here. So 1 minus r to the power of k. And that's all over 1 minus r. Okay. And all we're going to do here then is replace a with 10 and r with 2. Okay. So in that case, then we get 10 to the power of 1 minus r, where r is 2. So that's 2 to the power of k. And that's all over 1 minus r, so 1 minus 2, so that would give us minus 1 there. And this here then, the sum of the first k terms, that's equal to this number here. So 163,830. Okay. So now, well, I've got 10 divided by minus 1, that's the same as minus 10. So I get minus 10 lots of 1 minus 2 to the power of k. That is equal to this number here. 163,830. Now what I'm going to do is I'm going to divide both sides by minus 10. I get 1 minus 2 to the power of k. That's going to be equal then to minus, I get minus 16,383. Okay. I want to make this positive now, so it's minus 2 to the power of k, so I'm going to add that to both sides. What I'm going to do then is I'm going to also add this to both sides as well. And therefore what we get here then is 2 to the power of k is equal to 16,384. So what you'll notice here then is we want to show that k is equal to log 16,384 over log 2. At this point here, we're getting pretty close. I've got the 16,384. I've got this 2 here. So given that the answer involves logarithms, it would make sense now to take logs of both sides. Now, if I take logs here of both sides, I can bring the k down in front as well. So I get k log 2 is equal to log of this number here. And then finally, do it up here. I'm going to divide both sides by log 2 here. So in that case then, therefore, k is equal to log 16,384 all over log 2. Okay, as required there. And there we have it. So that's the solution there to part A. Like you can see, it can be quite tricky to begin with a question like that. But once you've seen an example or two like that, they all follow a very similar pattern. So that's part A done. So we're going to need to clear the screen here to have a go at part B. Now, even if you couldn't answer part A, if you couldn't show this, you can still attempt part B and part C. So for part B then, it says for this value of k, evaluate the summation of 5 times 2 to the power of r from r equals 1 to k plus 2. So this here is k. Now, if I put this into my calculator here, what I would expect is an integer value. So I quickly do this then. So log of 16,384, and then divide that by log 2. What I get here is 14. Okay, so therefore, k is equal to 14. So now, this summation here will have limits from 1 to 16 because it's k plus 2. So 14 plus 2. Let me just write that down. So from r equals 1 to 16 of 5 times 2 to the power of r. And then notice this here is our geometric series again. First term a is 10 and r is 2. So now we're going to find the sum of the first 16 terms, so S16. So in this case here then, that would be 10 times 1 minus 2 to the power of 16. And that's all over 1 minus 2, so 1 minus r there, where r is 2. All you need to do here now is just put this into your calculator here. And if you do this correctly, what you should get then is 655,350. Okay, so that's the number you should get there for the sum of the first 16 terms. Like you can see, part B is actually quite easy. You just need to understand that this value of k here is simply an actual integer. Then just change the limits and then just find the new summation. So that's the answer to part B. And then finally for part C here, it says briefly explain why the summation then from r equals 1 to infinity of 5 times 2 to the power of r cannot be evaluated. So this comes back now to understanding the sum to infinity for a geometric series. So remember, for the sum to infinity, we require that r is between -1 and 1. So let's just write that down. So for a geometric series, for the sum to infinity, we require, so sometimes you'll see this written slightly different. So this is mod r. So mod r is less than 1. So this just means the same thing then as between -1 and 1, like so. So because r equals 2 for this question here, or this series, so because r equals 2, this means then the series will be divergent. Okay. And there we have it. So that's all we need there for part C. Just briefly understanding, this condition here on R. So R needs to be between -1 and 1. So if we've got R equals 2, the series will be divergent. Okay. And that's all we need then. And that gives us the solution there to question 4. And finally then, if we take a look now at the very last question here, question 5, where we have a question on modeling with series. So what we've got here is a local property developer that began a 15-year program building new properties in a small town. The program started in 1990 and finished in 2004. The number of properties built each year forms an arithmetic sequence, and the total number of properties built in the first 6 years is 258. So for the first part then, part A, I want to show that 6A plus 15D is equal to 258. So for part A then. So what I notice here then is the total number of properties built in the first 6 years is 258. So that means S6 is equal to 258. So in other words, the sum of the first 6 years, the sum of the first 6 terms is equal to 258. And what I also notice here then is this equation that we need to obtain is equal to 258. So let's just start then with the sum of the first 6 terms. So don't forget the sum of the first n term, so Sm, that's equal to n over 2 times 2a plus n minus 1d. Okay, like so. So in that case then S6 here, which is equal to 258, then in that case I'm going to get n over 2, where n is 6, I get 6 over 2. We get 6 over 2. We don't know what a is and we don't know what d is, so we'll just leave those as they are. So 2a, n minus 1 times d. So n here, that's 6. So 6 minus 1, which is 5. So I get 2a plus 5d. And that's all equal then to 258. So here then, 6 over 2, that's 3. So I get 3 lots of 2a plus 5d. And that's equal to 258. So therefore now, if I expand this out here, we should hopefully get this here, which we're clearly going to. So 3 times 2a is 6a. 3 times 5d is 15d. And that's all equal to 258. Okay, so we've got 6a plus 15d equals 258 as required there. So that's the solution there to part A. Then for part B, it says in the 10th year of the program, there were 82 properties built, form a second equation in A and D. So what we're saying here then is using the formula then for the nth term, U10 is equal to 82. So don't forget the formula for the nth term, Un, that's equal to A plus n minus 1 times D. Okay, so therefore U10, that would be equal to A plus 10 minus 1 times D, so that's A plus 9D, and that's equal to 82. So therefore, for part B, then we get A plus 9D equals 82. Okay, so that's the solution there to part B. That's our second equation in A and D. And then finally for part C here, so let me just kind of split this off from part B and part A. So for part C then, it says, hence or otherwise find the number of properties built in the first year of the program. So what I need to find here then is the first term in this sequence. So I'm looking for A here. Now, I've got A plus 9D equals 82. I've also got this equation here in terms of A and D. So if I can kind of get one of these equations, so say, for example, if I rearrange this to be A equals, I can substitute that into this equation here, we should be able to solve for D. And once we find the value of D, we can then substitute that back in and find the value of A. Okay, because that's what we're looking for. We're looking for the number of properties built in the first year of the program. So if I call this equation 2 here, okay, that's equation 2, and this is equation 1. What I'm going to do here is rearrange equation 2. So what I'm going to get then is A equals 82 minus 9D. Okay. And what I'm going to do now is I'm going to substitute this here into equation 1. So sub into equation 1. Okay. So in that case, I'm going to get 6 lots of 82 minus 9d. We've then got plus 15d here. And that's all equal to 258. So now if we expand this out here, 6 times 82, that is 492. I get 492. 6 times minus 9d here, that's minus 54d. Minus 54d. And we've got the plus 15d here. And that's all equal to 258. So now if we collect like terms here, minus 54d plus 15d, that would be minus 39d. I've got 492. 492 minus 39d. That is equal to 258. So now I'm going to add 39d to both sides. I'm also going to subtract 258 off both sides. I'm going to get 39d. So 39d is equal to 234. And therefore then, d is equal to 234 divided by 39. That gives me d equals 6 there. Okay. We find the value of d here, the common difference. So in other words, each extra year, I should say, the 6 extra properties built. Okay. So in that case, then we can now easily find a by using this rearranged form here for a. So therefore, a is equal to 82 minus 9 times 6. Okay. So 82 minus 9 times 6, put that into your calculator, and what you should get here is 28. Okay. So in other words, the number of properties built in the first year of the program is 28 properties. So therefore, 28 properties built in the first year. Okay. And there we have it. So that gives the solution to C. That gives the solution there to the very last question, question 5. And that brings the end of this video on exam revision for sequences and series.